very happy to introduce our final speaker. You're going to get the introduction you deserve, Jim.
Thank you.
Okay. So Jim, also of Metron Incorporated, his research focuses on the problems in the defense and intelligence communities. His interests encompass the application of Bayesian methods to a variety of domains. These include test and evaluation, tracking and data association for kinematic and non-kinematic data, and the synthesis of classical detection and tracking theory with modern theory of networks. Jim holds a Ph.D. and master's in applied mathematics from Brown University. So let's please welcome our last speaker.
Okay, and let's see if this, show of hands, just get a background. How many people here have had a tutorial on Bayesian decision theory recently? Oh, very good, experts. Okay, and okay, here's a key question I want to ask. You're imagining, it's difficult to value a system that you're under test. You know, what's the total value of the system? I'm not here to address that, but say you could assign a value to it, maybe what people are willing to pay to build it. But now the question of, like, imagine conducting a single trial of the system. Like, how do you assign a value to that? That's a very strange thing to do. And yet, you know, if it were too expensive to fire off like a fancy, you know, there's on some expensive piece of equipment, you get like, nah, I don't really think it's worth it. So, but what that does, the value of a Bayesian framework and Bayesian decision theory, it brings all your assumptions into the light. So rather than have that decision being made, you know, by someone's gut, we're trying to answer this question with mathematical analysis. There are two halves to what I'm talking about. There's Bayesian sequential testing. This is essentially the Bayesian probability you just had the tutorial on, and the idea that you're updating this over time as new measurements come in. And then the utility function for the Bayesian decision theory, there's the utility function we like to think of, we're just calling it Moneyball, because a lot of people, if they haven't read the book, they've seen the movie. And the idea here is, rather than evaluating a baseball player, it's like, well, I like the cut of his jib, or, you know, he's tall, right? They're saying, how many additional wins per season is this guy going to give us? We would like to get utility functions that connect the value of the system to the value to the warfighter or to the mission. And we're calling our approach Dynamo. So Dynamo has two components. The first component on the left here is dynamic knowledge. It's knowledge that is updated over time as you do experiments. And on the right are the evaluation criteria. There are different criteria we can use, and Moneyball is just kind of the ultimate one, but there's a little asymmetry to what I'm showing you here. I'm showing you sort of 3 levels of testing model, 3 levels of evaluation. We're kind of taking the position that you should be using a Bayesian model, but evaluation criteria, you can use a whole bunch of different ones. That's fine. That's why in the end, we have these red arrows coming out from the Bayesian model to all the various evaluation criteria. All right, so I'll just get into what these different boxes are in this figure. Oh, and I'm going to tell you as I go through those boxes, the exemplar that we're going to use is the TPQ-53 counter battery radar. So the way this works, there's a radar. It's detecting something that's firing at you. Here, we're not, Adam with the Mach cannon, we're interested in the point of impact error. Here, we're interested in the point of origin error because we want to communicate that to a counterfire battery to take it out. So that's our key outcome that we're trying to measure. And there are various environmental variables like the range, the operating mode of the radar, the type of munitions being fired, the quadrant elevation, etc. So, you know, we ran some things on real data. I'm not showing you the real data here because we're keeping it fully on class, but I'll have sort of examples with faked data. Okay, so suppose we're setting up test and evaluation. And full disclosure, you know, I'm new to the test and evaluation community, so I'm no oracle. I'm like, here's how we do T&E. We are good at doing sort of Bayesian analysis, so that's my perspective. So So when I'm looking at how one does T&E, the first thing that I see is like, well, you can do a number of tests. You can pick different environments, X to test in, or contexts. You have a vector of environments, so like the range, the aspect angle, all these things go into the environment vector. And there's an outcome that you're interested in. This case is the log of the POO error. All right, and you could just say, okay, that's it. All we do is collect a bunch of data. That's what T&E is. And then you hand out data to some nerds and they do something. You know, that's one viewpoint. But I want to highlight that leads out a lot of it leaves a lot of open questions, like, well, what environment should we test in? How do we know if the system's good or bad? So really, this is only the very beginning of the process. So this lives on the testing side. And then on the evaluation side, like the first question you might say, hey, does this system meet requirements or not? Well, okay, then you have to refer to the temp, and then the temp for the TPQ 53, they divided things up into 9 sectors, and they told us, you know, they tell you what the PO error should be, what the threshold on that should be within each sector. Okay, well now you're starting, at least now you're defining what outcomes are good. It still doesn't answer a lot of questions, you know, again, like which tests would be good to conduct. It doesn't tell you at this stage, you don't have any notion of like, well, what if I actually use it in an environment they haven't explicitly tested? Like, what'll happen then? Like, there's no answer to that. Like, what do you do? Well, that's where you need a model. What a model is. A model says it takes in an environment X and gives you a probability distribution over the outcomes Y. Okay, well, that would be good to have. Where do we get one of those? Well, you know, that's where the technical expertise in modeling comes in. So in many models are parametric. You have some parameter vector theta. So Justin was talking about estimating theta. It's the same theta as Justin's theta. So in testing, we'd like to get a good estimate of what this theta is. So, okay, good. So once we have that, once we have a model, we can start to say, okay, when we collected these tests, I've sort of omitted a step here. I'm showing you here what you might interpret this as like, oh, I see 79% of my tests in this sector here of rockets, and the radar was in 360-degree standard mode. This makes it look like 79% of those were successful. But this is actually something a little more sophisticated. This is saying that would have been if we didn't have a model. Once we have a model, we're saying 70% of the environments in that region, if you conducted it for that environment, 79% of the time it will pass. So this is an important distinction, because now you can imagine, well, what if I do another test and it's going to be like a really hard test? I can be really far range. That's probably going to bring that 79% down. No, that's not what we're saying here. The 79% on average will still be true. It'll just say, if you're testing at really far range, the model knows that that's a hard thing to do, and it's not going to penalize you. So already having a model gives us a very robust notion of a compliance fraction. Adam introduced this concept. It's what fraction of the time are you meeting requirements? Okay, so having a model is good. Having a model allows you to do optimal design. You notice in the literature, if you look at the design of experiments metrics, there's just a whole alphabet soup of different optimality criteria. A lot of this comes from you have this covariance matrix, and there's different ways to kind of assess how big it is. Okay, well that's nice. Now that we have a model, we have a nice kind of principled way. The theory of optimal design goes back to hundreds of years, so there are lots of nice papers about it. But something kind of funny happens here. These boxes are all lined up. I've offset these boxes. And the reason for that is they're sort of different mindsets to what T&E is all about. There's a compliance mindset that says, well, I'm out here testing this thing. I got to check the box on whether the system meets requirements or not. And then someone higher up who's not out in the field will say like, no, don't focus too much on the requirements. Just gather all the information. The design of experiments itself, there's someone back, like doing all the math and says that this will be the optimal way to gain information. Well, those are kind of two different ways of thinking about it. So here's an example where neither mindset really captures what you're looking for fully. So we're imagining that we're testing something. Here, theta is going to be a scalar. It's going to be the hit rate parameter for a system. This could be for Adam's Mach cannon, like what fraction of the time does it hit? And it looks like the requirements say we want it to hit about 80% of the time. So now imagine that we're testing. In case A, you've done some tests and you have bracketed theta. Say it's probably between like 0.2 and 0.4 or something. And you're going to continue to do tests to tighten that up because, hey, it's better to tighten that up. Well, from an information mindset, good, you've tightened it up. From a compliance mindset, you would say, like, why are you bothering to tighten up to tell me just how badly you're failing to meet requirements? That seems crazy. So it's okay, all right, so we're going the requirements mindset or compliance mindset. But you get a similar thing in the compliance mindset. You say, okay, I have this kind of bracket. We're on both sides of the threshold. I better conduct some experiments to resolve that. And you see that you've like tightened things up, but you're still kind of straddling that threshold 50-50. And so what do? You feel like you've made no progress. You're just kind of like, yeah, 50-50 when passing or not. And so what can happen is people say, I guess I better test forever, you know, regardless of the cost of the test. So that's the central point that we're talking about in all this. How do you assign a value to a test? Like, when is a test valuable to do, worth doing? So there we have a paper on this in the Naval Engineers Journal, which should be out shortly. It's covered up a little bit. Okay. So that was optimal design. The next step, we had a model. Like, why do we need something more than a model? Why do we need this Bayesian model? Well, the problem is these parameters theta, you don't know what they are. No one's handing them. That's the whole point of testing, is to figure out what the parameters are, to tighten up your knowledge of what the parameters are. So in the Bayesian mindset, you always have some notion, you have some knowledge about what the parameters are that's expressed as a probability distribution, a prior probability distribution over theta. And what you do when you test is you're tightening up that probability distribution. So the shape of that probability distribution, I don't want to keep saying the probability distribution over theta. I'm just going to call that kappa. It could be represented as hyperparameters on some parametric distribution of theta itself. It could be some other representation. But whatever that knowledge is that you have about the parameters, it's encapsulated in some object kappa. So the Bayesian approach is to update this knowledge over time. Okay. Once we have this Bayesian model of what the parameters are, then we can do better analytics over here on the evaluation side. For example, looking at whether we're meeting requirements. I showed you something like this before, and this I think said 0.79 in here. The 0.79 is indicated by this green color, but now we have a size of the box. It's not just what our estimate of the parameter is, it's how certain we are in whether we're meeting requirements. So big box means we're pretty certain that's what the value is. And small box, if the box gets so tiny that you can't actually see the color, that's fine, because that means we have really no certainty at all about what the value is. So it's this comes from machine learning literature, the way of laying that out. It's working well for us. Okay, and then basic experimental design is, possibly a computationally difficult way, but an improved way of doing optimal design. Okay, so finally, MOneyball, I mentioned before. This is really the ultimate evaluation criterion we want to use. It's good for visualization purposes to show people your progress on meeting requirements. It's good to be able to design experiments. But ultimately, if we want to say what is the value of doing this test, we want to have that value not be some arbitrary thing. We would like it to have it be in units that are comparable to the units of the cost of doing the test, which is usually dollars. And so, if we can value the ultimate system in dollars and our decision about doing the test in dollars, we need at some point to have everything in a common currency. So, okay. So we will have a utility function that we're kind of calling MOneyball. Okay, and then if we have all that, then our testing decisions come down to weighing the benefit of our increase in knowledge versus the cost of doing a test. So, so how does this work? Oh, and we've branded this Dynamo. This is essentially the same slide. Okay, so now this gets into like the mathematically most meaty part of the talk. I hope it's like Adam's last slides were kind of painful. This is going to be painful. It's a different sort of pain, but we'll see. Not painful. You weren't watching, yeah. No, it's a lot to absorb. It's a lot to absorb, you know. Yeah, okay. This is going to be a lot to absorb too. Okay, so so what does knowledge of the system mean? Like, to use a common word like knowledge, there's a danger to it because people are like, oh, I know what knowledge is. There's knowledge in the temp, in the test data. The SMEs have knowledge. And so I want to, in this Dynamo paradigm that we're developing, I'm going to define knowledge as something that has 3 properties. And if you have those properties, like, I don't care about the particular form of the knowledge, but if you have these 3 properties, then you're good to go. So property number 1, if you have knowledge, you're able to predict what an outcome will be for any environment X that you choose to use the system in. Okay, well, do we have that? Well, this is a graphical model of kind of a generic Bayesian system. So it says up here, if you know the knowledge, there's some probability distribution over theta given the knowledge, because that's kind of what the point of the knowledge is, to represent the distribution. And so what you can do to show that you're providing a distribution on y, well, you could sample a theta given kappa, and then for any given environment, you can sample an outcome y given that x and that theta value. So you provide the x, you sampled the theta, the 2 of them together gives you a model. You have this likelihood model L of y given x and theta, and now you can generate sample thetas. So, okay, check, we're able to do that. You could also just use an explicit formula for the posterior predictive distribution if you can do this integral over theta. So, okay, so that's property 1, this predictive capability. Property 2, as each new data point arrives, the data point is an environment and an outcome y. As each new datum arrives, you need to be able to update your old knowledge to your new knowledge. Okay, that's fine. The examples that I'm going to show have this conjugate prior structure where that's very easy. And the examples that Justin was showing, you are kind of representing your knowledge as an ensemble of different thetas, and that's fine too. Those both count as updates. Okay, so together, when you have these 2 properties, what you have is whenever you have your old knowledge kappa, and you have some set, some data matrix X of environments that you're going to test in, you can compute the probability distribution of the new knowledge kappa plus. So that's the key thing that this is giving us.
So are we talking about priors or are we talking about something different?
This is talking about your kind of whole setup. And when you have this, so it's kind of the model structure, and there's going to have to be a prior to get it going. Just the Bayesian mindset, at any point in time, you have these probability distributions exist.
So, are you asking about the kappa?
Yeah.
Yeah, it's like that, like the mean and the variance that describe the parameter distribution.
The prior, if you want to specify prior, I would call that kappa sub 0, your initial value of kappa. And then over time it updates. Okay, and then the third property this knowledge kappa has to have, you have to be able to compute utilities of it for any given state of knowledge. Is like, well, how good is this knowledge? And you need to be able to define a utility for each terminal decision, which is a concept Adam introduced. So in particular, your terminal decisions could be, I'm going to reject this system, I'm going to accept it, put it into full rate production now, I'm going to send it back to the developer to improve it. And you have to have sort of models for, in any given state of knowledge, what the value of that terminal decision would be. Once you have that, now you can actually write down an explicit set of equations for doing utility updating. And they look like this, and they, they're fairly simple. It just says, the first three are very simple. It says, my utility of any state is the maximum over my utility of stopping now, U sub D, terminal decisions, or continuing to test, U sub C. And I can tell you UD is just the maximum over each individual terminal decision. So it just says I'm going to make the best terminal decision if I'm going to stop. Continue testing is just a maximum over, you have a set of possible tests that you could do, test matrices you could use. And then the only complicated equation is just saying that if you're going to do a certain test, now you have to take this expectation over how your knowledge will update. That's properties 1 and 2. It will allow us to do this. And then so it'll take utility of the updated, take the expectation of the updated utility minus the cost of doing that set of tests. Okay, and the issue with this is a recursive equation that just, to compute this, you have to go out to the kappa plus pluses, so how do we deal with that? Okay, I have about 5 minutes left.
You got 7.
7. Okay, well then I will try to address this slide. Okay, so it's important that the key thing here is you need to formulate the utility U sub D of kappa for every terminal decision D. So a typical terminal decision is you're going to accept the system and build it. How do you actually define the utility for any state of knowledge by the parameters for that decision? That's a daunting task because kappa is kind of a complicated thing. So it's important to understand it has a specific kind of structure which helps us. So every time you have utility of kappa, a special case of that is, well, what if you had exact knowledge? That's one of your kappas, is I know that theta is exactly this. So we can kind of overload the symbol and just have it operate on theta directly as a special case. And then if you have the knowledge of the utility of the system, if you knew the parameter theta, well, you can kind of lift that to a utility for your knowledge. You could say, well, one way to do it is you just take the expected value over all of these. That seems like a reasonable thing to do, but you don't get back to the original one of these. You get something else that we call an intrinsic utility. And so any utility function you specify, you can decompose it in the utility into the intrinsic utility, which you can compute this way, minus some other term, which we call the cost of imprecision. We like these intrinsic utilities. They seem to distill the intrinsic quality of the system. And this leftover cost of imprecision, this tells you about kind of knowledge that you're gaining about the system for its own sake. Yes, okay. And now the intrinsic utility, it has this martingale property, which says the expected value of it does not increase over time. It stays exactly the same. So you contemplate doing a test. If you're using intrinsic utility, like after doing the test, if right now the value is 5, after you do the test, your expectation is like, well, it could be 7, it could be 3, but on average, it's going to be 5. Now this sounds like, well, why even bother to test if my value is not going to go up? And in fact, the reason for this, if you only have ever had one terminal decision, if it were preordained that you're going to accept this system, and you say the current value is 5, what's the value going to be, after I do 10 tests? It's like, well, 5 on average. You'd say to yourself, why bother to test? And indeed, why would you bother to test if there's only ever one preordained decision? So it's actually doing the correct thing. So the value of testing that's coming out from one of these intrinsic utilities comes from where there's a clash, where there's 2 possible decisions. And the impetus to test arises from those regions. So here, I'm showing a case where I can plot out the best terminal decisions. This is there's kind of a lot to define here. Here, kappa has 2 components, A and B. So I can plot out kappa space in this 2-dimensional triangle here. A and B, you can think about like it's the knowledge if A is 60, that's like you flipped a coin and got 60 heads. And then B, 20, maybe you've seen 20 tails. And so what would that be here? 60, 20, you'd say, that system's okay, but send it back to the developer for improvement, right? That's the yellow improve region. And so the space of terminal decisions is shown over there. And so what I'm saying here is that there's a quantity that you can compute that is kind of the impetus to test, and it is only non-zero at these decision boundaries. So it has a specific formula. And then what happens if you actually then say, well, these are my optimal decisions, my optimal terminal decisions, but what if I have the option to continue to test? Well, that's over here. Here you get some gray regions that say, yeah, there it's better to continue testing. And you can see here that it's like these regions here where there was an impetus to test, they sort of diffused out and became a continue to test. The case I was showing you was a simple hit miss or coin flipping type of example. So these are details of that. So we set up an explicit example where we have reject, improve, and accept utilities. They're plotted out there. But what I want to show you, and so here's visualizations of these decision charts to tell you what the best thing to do is. And it's a function of decreasing cost. So if the cost of testing is infinite, well, we never test. As the cost decreases, then more and more of the time, it's better to continue testing. Okay, and so we can compute these. We had no notion kind of analytically what was going on here. It was just this like computational procedure. Before I tell you that, I'm going to enhance these plots by actually, instead of just having a gray, I'm going to show you this. I said there's this sort of impetus to test, this diffusing out from these decision boundaries. This shows you like what those values are. And you might say, well, that's actually more interesting than the decisions themselves. Well, we can change the color scheme so we can really see what this impetus to test looks like. And then, I wanted to know, like, if I come along here, I can just like plot it here on an actual graph so I can actually see what it's doing. And when we do that, we get these kind of funny spike shapes. And the neat thing about that is that we're actually able to compute analytically what the limiting form of that shape is. There's a formula there. It's broken down here. It involves, it's kind of covered up. There's an incomplete gamma function. But we're able to write it down exactly. And so you might say, well, why are you doing all this? It's still just coin flipping. What we're looking for here, in what Adam showed you, and I'm sorry I kind of said it was hard, but anything where we're kind of like iterating out into the future indefinitely is just a difficult procedure, right? It's computationally difficult. It's conceptually difficult. What we're looking for here is these kind of nice, we're going to be doing some approximation at some point, but what this is pointing to is just identify your terminal decision boundaries, and then your impetus to test, it's going to be bigger the closer you are to those. So if you're fully within the like reject region, there's no real impetus to test. You're going to end up rejecting, you know that. But if you're kind of near one of these boundaries, it's saying you should probably be testing. Well, how fast does that impetus to test fall off as you move away from the boundary? Well, it seems to have what shape like this. And we haven't shown this yet, but we believe this shape is not specific to the beta Bernoulli type of testing. We believe there's kind of a central limit theorem type of thing going on, so that we could take this and apply it to other cases. And it's going to be somewhat heuristic, but we're trying to identify the phenomena that are really at the heart of the impetus to test. And we're developing Dynamo to implement those methods. And so now I must be out of time. And I'll just kind of like, there's some other stuff in here, and you'll have all the slides online. So, that's what our GUI looks like. And look, I finished. Okay. All right, any questions before we get lunch? Yes.
Last one. You generated something that I think you called the terminal boundary, and then you said like you can go from the boundary and project backward. Like, what are examples of something that you could use to actually figure out what that boundary is? Like, could it come from you have a certain amount of budget to test, so at most you could do this many trials? Could it come from something else?
In the original, when I made plots like this originally, I just said, like, let's suppose you have a budget of 100 tests, and then these gray regions pinched off at the boundary. And but lately, I just thought it'd be cooler to just project these things all the way out to. I had to do like 10,000 for some of these, and eventually they pinch off on their own because and then I just kind of cut them off here to show them. So there's the reasons I like these better, but.
In practice, though, what I'm hearing is who would say, here's the test, here are the resources that I have, here's the budget, you could form some constraints,
Okay.
and then that would inform what these boundaries are.
It informed them. It makes it easier, actually. Yeah. So that's why I did it first. Yeah.
Your constraints making something easier.
Well,
Then you can hear that.
if you have to go out to like consider like testing forever, that's hard. Yeah. Okay. Anything else? All right. Thank you, everyone.